This is a short lecture on Newton's three laws of motion. Newton's first law states that a net force is required to change an object's motion. This is called the law of inertia, and it's often stated that an object in motion will stay in motion, and an object at rest will stay at rest unless a net force acts upon it. What this is saying is that objects can stay at rest and objects can stay in constant motion without any forces acting on them whatsoever. It's also true that many forces can act on an object, but they can all cancel each other out. For example, right now I'm sitting in a chair, I'm not moving at all. But gravity, the force of gravity, certainly is acting on me, but there's also a force from the chair that's acting against gravity, perfectly canceling it out so that I stay still. Another example of something in constant motion is if you imagine a car driving on a very icy road. The driver might try to use the brakes to stop the car, but if there's no friction between the tires and the road, then there's no stopping force. The brakes don't work. And so even if the driver stops the wheels, the car continues in motion, and there's no force pushing it. It just continues with the same motion that it had when the driver stopped using the engine and started using the brakes. That motion will continue until the car hits something or until the car reaches a patch of road with friction so that the force will stop it. Here's a question to consider. If you know the net force acting on an object, can you describe the motion? Well, let's think of an example. So I'm going to draw a car. There it is. There's my car. Let's give it some more windows. Maybe a door. All right. So there's my car, and weight is certainly pulling it down. That's a force, but there's also a force from the road pushing back up, and so it's not moving up or down. But I do know that there is a force acting on it, and the force is pointing in this direction. That's the direction of the force. Force is a vector. So can I say which direction this car is moving? Can I describe the motion? No, I can't actually, because even though this force is directed so that the car should be changing its motion sort of to the back in this way, I don't know if the car was moving forwards or stopped or moving backwards when this force started acting. This could be the force of the brakes, but if the car was already stopped, then this wouldn't really accomplish anything. If the car was moving forward, then the car would still be moving forward but slowing down. Or this could be the force of something pushing the car so that it actually moves backwards. Net force and motion are not the same thing. The net force describes a change in motion, but not the motion itself. Newton's second law is an equation. It says that acceleration is equal to net force divided by mass. So the acceleration is the change in motion that we see in the object. That was described by Newton's first law. So the change in motion that we expect to see is proportional to the sum of all the forces. That's the net force, the overall force acting on the object, divided by the object's mass. So what this is saying is if we have two identical objects, they have the same mass, but one has twice as much net force acting on it, we would expect twice as much acceleration. Meanwhile, if we took an identical force, an identical push, and pushed one very small object with low mass and one very large object with high mass, we would get more acceleration on the low mass object. Imagine a motorcycle and a dump truck. What if you swapped those engines? I know it's not really physically possible, but let's extend our imaginations and try it. If you put that hugely powerful dump truck engine in that motorcycle, the amount of force that engine provides, that motorcycle could accelerate at extremely high rates. Meanwhile, that dump truck with that little tiny motorcycle engine with its wimpy little force trying to move that huge mass, you would get tiny, insignificant accelerations. That's what Newton's second law is explaining. A question to consider is, what is the difference between mass and weight? Newton's second law, the equation we just looked at, specifies mass, not weight. Well, it turns out weight is a force. Weight is the force of gravity acting on an object. Meanwhile, mass is related to the amount of stuff in an object. Comes down to the number of atoms in the object, really. This is how an astronaut can go to the moon, and maybe she doesn't actually change size at all. She's still got the same number of atoms in her body that she had on Earth. She's got the same mass, but she weighs considerably less. There is a force of gravity that acts on the moon between the astronaut and the moon. It holds her down, holds her feet to the moon's surface, but it's only 1/6 of the strength of gravity on Earth. And so if this astronaut weighed 120 pounds on Earth, she would weigh 20 pounds on the moon. Pounds are a unit of force, a unit of weight. Her mass, however, the number of atoms in her body, would be just the same on the moon as on the Earth. Newton's third law says that forces are always produced between objects, and that the force produced between two objects acts on each object with equal strength but in opposite directions. This law is often stated as for every action there's an equal and opposite reaction. Although that's kind of counterintuitive. We don't really see that in our day-to-day life. What Newton's third law claims is that the force which pulls this boy down towards the Earth is actually the same strength as the force which pulls the Earth up toward the boy as he's falling. That's not usually how we think of it, because we very clearly see the boy moving, and we don't really feel the Earth moving when this boy jumps into the pool. That's because there's a difference in acceleration. Remember Newton's second law. When the same force acts on two objects, the object with less mass accelerates more. Well, this kid's mass is less than the Earth for sure, and so he is going to accelerate a lot more under the same force compared with the Earth itself. So we don't see Newton's third law in action very much in day-to-day life. Where it is noticeable is in cases like firing a gun. The recoil of the gun, which moves backwards as the bullet moves forwards, that's due to Newton's third law. Another example is astronauts in space have to be tethered down. They have to use handholds and footholds when they're working. If they were freely floating and were trying to turn a screwdriver, as they tried to twist the handle, their bodies would twist in the opposite direction, and they would never actually be able to turn anything unless they were able to get a grip on a third object and use that as leverage to complete the twisting motion. A question to consider is, how does Newton's third law explain how jet engines work? This is a cross-section of a jet engine, the type that's on a jet airplane. Air comes in and is mixed with fuel being burned, which heats the air considerably, and then turbines help force the air out towards the back of the plane. What's happening here is that a lot of air molecules are being accelerated by a huge force. Here, the force is pushing the air out. The air pushes right back on the turbines, which forces the airplane forward through the air. Anytime that an airplane goes overhead, you should realize that that's a great example of Newton's third law at work. Here's a final recap of Newton's three laws. Newton's first law of motion states that a net force is required to change an object's motion. Newton's second law states that acceleration is equal to the net force acting on an object divided by the mass of the object. And Newton's third law states that forces are always produced between objects, and the force produced between the objects acts on each object with equal strength, but in opposite directions.